Okay, so let's start our introduction, and we will start from our standard form. So we want to define one kind of linear program, and we will call it the standard form. So the standard form linear program is a special type of linear program. If we say it is a standard form, then the following things must be true. All the right-hand side values are non-negative. All the variables are non-negative. And all the constraints are equalities. Okay? So right-hand side may need a specific definition. So right-hand side is the RHS is the abbreviation of right-hand side. That somehow means when you are given a constraint, we typically always put those things that are associated with variables, we put it at the left-hand side. And then the only constant, we put it at the right-hand side. Okay? So if we do that, pretty much the right-hand side is just the single constant. And we would always put the constant at the right-hand side when we are doing linear programming formulation. Okay? So suppose we do that, it doesn't really matter whether you have less than or equal to, greater than or equal to, or equality. We always call the right-hand side, that single constant, a right-hand side. Okay? So we also mentioned that there is no restriction on the objective function. So it doesn't really matter whether you have maximization or minimization, whatever. So all the requirements are on constraints. So somehow we need to convince you that for any linear program, we may convert it to a standard form. So let's try to do this. So the first requirement says that all your right-hand side must be non-negative. So I hope this is not too weird for you. As long as you have a negative right-hand side, let's switch the two sides, or let's flip the sign for the two sides. Okay? So suppose we say you have 2x1 plus 3x2 less than or equal to negative 4. All we need to do to make this guy positive is to multiply each side by negative 1. Okay? And once we do that, we're going to say, okay, negative 2x1 minus 3x2 must be greater than or equal to 4. Obviously, these two constraints are equivalent, so we don't really change anything. All we did is to change the right-hand side to be non-negative. And we can do that for any constraint. And then we need non-negative variables. So if a variable actually is non-positive, we may replace it by, again, negative x1. So for example, if you say, oh, okay, 2x1 plus 3x2 must be less than or equal to 4, and your x1 is non-positive, then all we need to do is to replace your x1 by negative x1. Then that new x1 would be non-negative, and your constraint would be fixed to negative 2x1 plus 3x2 less than or equal to 4. So again, we don't really change anything. We simply change the sign of these variables. One thing that may be not so intuitive is the case that when your xi is free. So suppose you have a free variable. It may be positive, negative, or whatever. We may again replace this free variable by two non-negative variables. And we would set xi to be xi prime minus xi prime prime. So somehow these two new non-negative variables, we may use their difference to express xi. And intuitively, this one means the positive side, and this one means the negative side. So what does that mean? That means if your original xi takes a positive value, we would let xi prime to be that positive part. If it is negative, then we would take xi prime prime, make it a positive value, so that the negative side of xi prime prime goes back to your original xi. So an example may be even more easier to understand. Suppose you have a constraint like this, and your x1 is unrestricted in sign. Then we replace x1 by two other variables, xi prime and x1 prime prime. They are all non-negative. and we replace x1 by x1 prime minus x1 prime prime. So we also modify this constraint. Then how does that work? It doesn't really take away any flexibility. Your xi, original xi, may still be 5, for example. Then your xi prime is 5, xi prime prime is 0. That's fine, right? Your xi may be negative 8. Then you would have xi prime to be 0 and xi prime prime to be 8. So somehow after this conversion, any possible value in your original constraints may be expressed by your new setting. So it doesn't really take away any flexibility. How about your requirement 3? Requirement 3 says all the constraints should be equality. So for any less than or equal to constraint, we're going to add a slake variable. And this slake variable somehow express what's the difference, what's the gap between your variable's value and that right hand side. Okay? So this slake variable may be added into this constraint while it is non-negative, so that the constraint becomes an equality. If you have a greater than or equal to constraint, typically we say you may minus a surplus or excess variable, okay, like this x3. So you say, okay, the left hand side is greater than the right hand side, then we add this x3. We subtract your left hand side by x3 to make the thing equality. So in all cases, you may see that either your slake variable or your surplus variables, they have physical meanings. The meaning is that, well, x3 either is a slake or is a surplus. It is representing the value of the gap between the two sides. Okay? So for ease of exposition, in this course, we will always call all of them slake variables. Somehow it's just filling the gap between the two sides. Okay? So we don't really specifically use surplus or excess. It's just some notions that some other people may use. But we always use slake variables, either this one or that one. So it measures the gap between the left hand side and the right hand side, and you will see it very often.